Hello guys, welcome back to this video series on pre-processing resting state fMRI data. So in this video we are going to see temporal regression. So in the previous video we saw how we could extract the mean white matter and CSF time series. So now we are going to use these mean CSF white matter time series to regress out the signals that are in the brain. So the time points in the brain. That is what we are going to do today. So before everything, let me just show you the image that we have right now. So I'll use Afni to do that. So I'm in my WSL screen, and here I've already uh, put the location of my func folder, that is the folder where my resting state files are. So what I'll do is I'll just type Afni. Right, so here you can see the Afni has opened up, and this is the R sub image. So we saw that we have in the previous video we have extracted the white matter and the CSF uh, signals or time series, and we have taken the mean of that from this particular data, the R sub data. This one. Okay, so now we are going to regress these time series, right? So if you see the graph of this particular data, you can see this unusual dips at certain places. uh, those are more prominent somewhere over here. You can see these dips, unusual dips. So if you remember, this was also due to the motion that we had corrected in an earlier video, right? In the realignment video, we had corrected this motion, but still the contrast because of that motion change was still reflected over here, right? So this is something that we have to correct now. So this is the image. Now during temporal regression, what we are going to do is we are going to go from this corner, that is the first voxel. We are going to scan the entire slice. Then we'll start over here at voxel 0 comma 0 comma 0, and then what we'll do is we will take the time series. So now this actually has no time series, but then so since this is a brain region, it does not have any time series. So it is actually foolish to regress this particular thing, right? So actually what we want is we want to just regress the time series that are inside the brain, right? So ideally, if we don't know where the brain is, we would have to scan each and every voxel and regress each and every time series of each and every voxel, right? Which is not correct. I mean, so you can see over here there is some signal that is present, but this is not the brain signal. This is some noise that is there over here, right? Because here this is not a brain voxel, and still there is some time series present over here, right? So the motive over here is to just regress time series or voxels which are inside the brain. We just want to regress these ones, right? We would not want to regress any time series that is over here which is not in the brain, right? So for that what we'll have to do is we'll have to first create a mask. So MATLAB does not know which are the time series that belong to brain and which do not belong to the brain, right? So for that we will need a mask that tells us that only the regions which are inside the mask are or belong to the brain, and which are outside the mask do not belong to the brain, right? So for that, first we will create a mask around this brain that will help us regress only the brain voxel time series. Okay, how to do that? It is very simple. What you can do is, so go to your WSL console or terminal, and over here there's a very simple function, 3D auto mask. 3D auto mask is a Afni function to give the mask of the brain. Okay, it has an option prefix. So here you have to type what name do you want to give the mask file as. So I'll keep the name as restmask.nii, and then you have to put the input file over here. So our input file will be this one, the where did it go? Yeah, R sub 10225 task rest, this one, right? So I'll write R sub, press tab, automatically it will come, and I have to write NII. So that is a NIFTI file. Okay, just press enter and you're done. You've got a mask. It is that simple. I'll show you the mask output as well. So over here, what I can do is I can press either I can do an underlay and show you the mask. So this is the mask. But what else I can do is I'll just keep this input file over here, the rsub file, and overlay rest mask. So here it has overlaid the mask over the input file. You can see how beautifully it has extracted or segmented the brain, or it has masked out the brain. You can see how beautiful is this brain segmentation. So this is how you can actually mask out the brain. And now only the regions that are in this mask, or only the values that are 1 over here will be regressed. All the values over here will not be regressed. So this saves time, and this also ensures that you are only doing regression on the brain voxel. Okay, so this is a very important step that you have to do before you do regression, or else if you don't do this step, if you don't do the masking, what will happen is you will in turn have to regress each and every voxel over here, which is more time consuming, and you may also you may also lead up with an error if there is some nan value or something else over here in the background. Okay, so that's the first part where we have created a mask. Okay, the second part, so let me just close Afni for now. For the second part, that is a temporal regression, what we'll have to do is so I've written a script over here. So this script will make sure and it'll do the temporal regression for you and make sure that everything is fine. Okay, so again I will execute this step by step so that you understand each and every step. So the first two lines are quite clear. Here I am defining the anatomical folder, and the second is defining the functional folder. So we have two folders if you remember. So this is my data set that I'm working on, and there is an anatomical folder and a functional folder to this. So I've just kept both the paths over here. So just let me press one. So you can see there's two variable anat and func folder where the paths of the respective folders are stored. Okay, now I'm going to the functional folder. So we'll be dealing with the functional folder only for the most part. So now I'm inside the functional folder. This is change directory. Okay, so the first thing that I want to do is, so I will extract any one volume. Over here I am extracting the 15th volume, but you can load any one volume. Okay, this is only for header purposes. I will use this value here below somewhere over here. So this is just to make sure that the header, the NIFTI header, I have also talked about a NIFTI header in one of my previous videos. So the NIFTI header tells you about some metadata of the NIFTI file. So just to make sure that the NIFTI header does not change in the new regressed image, for that I am doing this. I'll come back to this. Okay. So what we are doing is first loading the image using SPM volume function. Then we are reading the particular volume and we are taking its dimension. Okay, this is it for now. I'll come back to this when I come over here, when I'm actually writing the header file. Okay. Now here we are loading the mask that we just generated using Afni. So let me just press tab. So here I have first got the list, that is the volume, sorry, so mark list has the volume, SPM volume, it is reading the volume, that is the header file. So if you see mask list, it has the file name, it has these metadata and the NIFTI file over here. So again, when I pressed it, so the rest mask now you can see over here is a 3D mask, you can see, and the data type is double. Okay, so this is this mask, the mask that I just generated. Okay, now I'm loading the time series. So this will be my R functional data, that is my R sub image that I'm first loading. I'm using NIFTI read over here. So there are two options. You can also use SPM wall, or you can also use the inbuilt NIFTI read that is from MATLAB. So I'm showing you both the ways. Okay, now what NIFTI read does is it does not change the data type. So if you see Y image rest, so Y image rest is an int 16 variable. So since others are in double, I'm just making everything in double. So this is just changing the data type to double. Now over here, NT is the number of time points. So now if you see Y image rest, I've already loaded the 4D NIFTI file over here. So what I'll do is just extract its fourth size. Okay, so if I just let me show you the size of Y image rest. So the size of Y image rest is 64 cross 64 cross 34 cross 152, right? So this 152 is the number of time points over here, and that is at the fourth place, hence comma 4. So this will give me the number of time points. Okay, so here you can see number of time points is 152. Okay, next what I'm doing is, it is also a very good idea to regress the motion parameters. Okay, if you remember, while we were doing realignment, there was this text file that is the motion parameters as to how much a particular volume has moved. So in displacement and rotation, all those values were there over here as a text file. So we are also going to use this. So we'll also assume that this was also a noise, and we are going to use them also as a regressor. Okay, so if you remember this theory video where I had discussed why is regression important, over here we had, there was this and some more as well. So this is the mean CSF time series, the mean white matter time series, and there were some more, right? So we'll the some more is what I'm going to use over here. Okay, so this some more are nothing but these motion parameters. Okay, so here first I'm loading the text file, that is this motion parameter file. So I get a text, so this is just getting the path of that text file. Okay, so full file gives you the path of the things that are inside, and dir will give you the whole path. So if you see, I've just put a star over here, and I'm not written the name rp sub etc, right? So since this was the only text file over here, I could do this. Okay, this is another way to handle file operations in MATLAB. So a text txt file has the whole text file or the path of this rp sub text file. Next what I do is I load that particular text file like this. So text file dot folder, if you see the text file again, so text file dot folder will give me its directory or its path, and text file dot name will give me its actual name, the file name. Okay, so that is what I have put over here, text file dot folder comma text file dot name, and I get the full file path of that, and then I load that particular text file over here. Okay, so if you see rp rest 1, it will be these motion parameters that I get. If you remember, the first three were displacement parameters and the last three were rotational parameters. Okay, now here I'm just taking the first NT time points. So there were 152 rows only, but if in case there is some problem, then you will just take the first NT time points, that is the first the total number of time points that you have. Okay, now it is a good idea to also Z score them, because their mean and their variance may be different, and anyways we are going to regress it further, so it is a good idea to just Z score these particular values. So if you see rp dot rest, now these are Z scored. So initially the displacement could be anything, but now these values have a zero mean and a unit variance. Okay, all these values actually. Okay, now over here what I'm doing is, so here this is rp previous underscore rest. So here I'm going to put the value of the uh, previous volume. Okay, let me just, so this starts with zeros. Let me just put a step, and if you see over here it is end minus 1, that is it will go from 1 to n minus 1. Okay, let me just open this previous rest and rp rest. Let me put that side by side. Okay, so this is rp underscore rest and this is rp previous rest. So if you see for the first volume, so this is the displacement parameters and the rotational parameters for the first volume. So it is minus 2.109 something. If you see for this it is 0, because previous this there was nothing, so it is 0 over here. But for the second volume it is minus 1 1 1 and so on. For the second volume the previous parameters are minus 2 1 0.08 and so on. So this is like the previous values of that case. Okay, so it, so there is a paper, I'll link that into the description, that says that these are also important regressors that can remove noise from your data. Okay, so this is the other thing that we are going to use as a regressor over here. Next, so here I have one matrix that has all the regressors. First, that is rp rest, that is the motion regressor that we just saw. Then rp rest squared. It also turns out that the square values sorry, the square values are also important. So the square values are also regressor, the previous values are also a regressor, and previous value squared is also a regressor. So in all over here if you see rp auto rest, so there are 24 regressors that we have for now. So by regressors what I mean is I have 24 such these noise time signals that I'm going to regress from a given voxel time series. Okay, so I will have beta 1, beta 2 up till beta 24, and these are just the motion parameters. Our mean white matter and mean CSF is still remaining. So that is what we are going to do over here. You remember we had given a mean underscore W white matter underscore CSF rest dot mat in the previous video, which is over here, right? So this is where we are going to load that. So I've loaded that into a COV file. So covariance. So this has the two mean CSF rest time series and mean white matter rest time series over here. Okay, so this two I'm going to extract. So cov file dot mean WM rest will give you the mean WM rest. Cov file dot mean CSF rest will give me the mean CSF rest. Okay, and over here it is also a good idea to just calculate the mean of our input image, that is y image rest, that is nothing but this r sub image, and then later we will add it back. Okay, okay, now over here we are going to actually regress the time series. We have all our regressors over here. We have got the white matter mean, the CSF mean, and the motion regressors over here. Okay, so this is now going to go from x to in x direction, y direction, and z direction. So let me just again open Afni so that I can better explain. Right. So as I mentioned, so first we will consider the top left voxel over here. Slowly we'll go in this direction, this direction. So there will be a loop that will go from I is equal to 1 to whatever this last voxel value is. So this is the first for loop. Then the second for loop will go from here to here, and the third for loop will go in the z direction, say from here to here. Okay. So since this is a 3D volume, you have x, y, and z directions, right? So for them, these are the three for loops. So there is vi for one direction, vz for vj for the other, and vk for the third direction. Okay, so these are our three things. And then there is this dot that I'm printing just to make sure that things are going fine. Okay, I mean you could print anything over here; it doesn't matter. Okay, now if the rest mask is 0, okay, if the rest mask that we have created, if the value at this particular voxel is 0, let us just check what is the value now. Okay, it is 0. That means this is not a brain pixel voxel, not a brain voxel. So as you know, we start from the top left corner. So this is mostly a background pixel. I mean your brain will never start from here. So since it is not a brain value, you don't need to regress it, right? You just can put a trail of zeros over there. Okay. So here, since it is not a brain part, hence you'll just put it 0. I mean, all time series would be 0. Okay. And then, I mean, since this mask was 0, it never came over here. This else part is the regression part. Okay. So like this, it will keep on doing till it encounters a brain voxel. So what I'm going to do is, let me put a breakpoint over here. Oh, I just saved. There is this gray breakpoint that you can see. Now this happens when you have done some change in the file. So while I was executing the code, maybe I just changed something. I put a comma or something. So if you change the file, so then, because now this is a new file, the MATLAB is not going to stop over here, and hence it is giving a gray point. So what you can do then is just save the file. So this star also says that the file is not saved. So just save the file. When you save the file, the execution will stop. Okay. So you'll have to rerun the entire program again. So let me do that first. Let me clear anything. Okay. Yep. Okay, so now we are over here. So now we have encountered a voxel which is inside the brain. Okay, so if you want, you can see what are the voxel values from here. So the voxel values are as follows. We are in the ith direction at 11, the jth direction 26, and the kth direction 17. So at this particular voxel, the mask is 1. Since the mask is 1, it did not go into the if loop. It went into the else case. And over here, what we are doing is we are merging the white matter mean. Oops, sorry. See, I again changed the file, right? So because I then pressed Control Z, that is undo, I am now in the original file. So this again turned red. So this is the white matter mean, the CSF mean, and the auto rest, that is our motion parameters over here. Okay, so in all, if you see, B is a 26 regressor set. So in all, we have 26 such regressors that we are going to run, and 26 beta values we are going to get. Okay, but we are not interested in the beta values now. We are just interested in this residual signal, the error signal. Okay, so here it is also important to do z-score so that all regressors have zero mean and unit variance. And then there is this regress function. You can search MATLAB help and see what the regress function does actually. But in simple layman terms, what it does, it takes the input. Okay, so here I am giving it the input y image rest, the ith, jth and the kth voxel, all the time series. So colon means all, so I am giving it the entire time series of this particular thing. You can just check this. So if you see the answer, so this is it is giving you 152 values, 152 time series. But the problem is over here, if you see the answer, it is still a 4D double. It is still a 4D double, and this actually needs a one dimensional signal. So what it is doing is, it is having four dimensions. The first three dimensions are just one, and then the fourth dimension is this. And we don't want it like this, right? We wanted a one dimensional signal so that we can put it to regress. Hence there is shift dimension that we use, and shift dimension will give you a 152 cross 1 double. Okay, so for that, shift time is important. And then these are our regressors. Okay, and then you also have to put all ones at the end. So if you see this, so you in all have 27 columns or 27 regressors, where the last is just one. So this is for the bias, or this is like where you don't, so this is some offset or some bias from the signal. For those who don't know regression nicely, it's okay. I mean, you just need to put this trail of ones at the end. Okay, and that's it. I mean, you just execute this regress. What will give you is the b value, the other values. So whatever, what we are interested is in this third value, that is the residual signal. This one, the residual signal. So we are just going to use the residual signal that is over here, and that's it. I mean, so slowly our y image rest regress is getting created somewhere over here. This will also be a 4D double, obviously. Okay, and like this, we slowly execute all the different, you can see the dots are coming over here because of this. So we are executing all for all the voxels and regressing out everything, I mean every noisy element that we have over here, and it has done. You can see it was not too long. So that's done. Now we clear any, so we are going to use a v variable. So if there is any previous instance of v, we just remove that. And now we are going to put the header information. Okay, so if you just let me just open one of the SPM volumes. So here we have an SPM volume v pair rest. So if you see, these are some header information. It is very important to keep this as well. Okay, so the dimension, the file name, the dt is the data type. So what I have done is I have put all the values over here. So what does vfmain do? It is the file name of the image, the dimension are the x, y and z dimensions of the volume. Then there is a dt, which is nothing but the data type. So like there's double and so on. So this dt gives you the data type information. Then there is this mat. If you remember in the co-registration video, we had used this transformation matrix. So this is the same transformation matrix that we had estimated during the co-registration video. So that is over here. It is very important to give this, because if we don't give this mat, the final output image will again have to co-register that to the native space. Okay, so this is very important. And there is something known as plain info. You can read about it over here. Okay, so these are the important header files that we require, and this was where I created. So in the start of the video I told you to just choose any one image. So this is 15. I mean, this can be anything, you can do it one as well. So take any volume and copy the data, header data from that volume to over here, so that the header is consistent throughout. Okay, So here I am putting all the header info. Then here I'm going to write that particular NIFTI file. Okay. So in the header there is also something known as N. So if I just start this, so this N tells you the volume number. So since I had extracted the 15th volume, here it shows 15. Okay. So for that I will have to do it manually. I mean through a for loop, because for the different time points, the 152 time points, not everyone can be 15, right? The first should be 1, the second should be 2, and so on. The 152nd will be 152nd over here, right? So accordingly the n value will change for every volume, and that we are doing it over here. We are putting the file name over here. So what I'm doing is I'm just adding a reg underscore in the front, so that we understand it is a regressed time, it is a regressed volume, and that's it. I mean, let me just continue. This might take some time to write. Yeah, it's done. So now we have got a new volume, that is the regressed time series volume, and let me show you how does it look like. Right, so it is saying added one more data set, that is the regressed time series data set. Okay, let us look if the regression is good or not. So let me just compare it with our previous case as well. So you remember these dips were the problem, right? These dips over here. This, we want to remove these dips. Okay. So to remove these dips, we have done regression, and when you see the regress output, you can see the beauty over here. All those dips are gone. All those dips are gone. You can see this. All these are gone. A beautiful time series. Also, if you see, there are some unusual trends as well. You can see this trend over here, unusual trends. So this is also gone in regression. So in the regress time series, you can see there are no trends. These are just time series that are ready for analysis, right? So you can just compare both of these images, and then understand the importance of regression over here. Okay, so that's all for this video. In this video we have successfully regressed the time series, and now this is a very nice clean data, but still this is just in the native space. So if you would have 10 subjects and you want to analyze 10 subjects data together, you cannot have all the subjects in their native space. Okay, then you'll not be able to analyze or group them together and do something, right? So for that we'll have to put them into the standardized space or the MNI space or the normalized space. Okay, so that normalization video is going to be the next video, and stay tuned for that. Thank you so much for watching. Thank you.